In this video, I'm going to talk about a curl. So curl is the last property we're going to talk about for the vector field. So in the previous video, I talked about the divergence, which is talking about how diverged the field is at a different position or different point. So curl is another property is related to the rotation of the field. Okay, before talking about the physical meaning, first let me talk about how we actually compute the curl of the vector field mathematically. Then I'll talk a little bit about the physical meaning. Then I'll give you a few examples. Alright, so curl mainly talk about the property for a 3D, only a property for a 3D vector field only. So it doesn't apply to high dimension like 4D, or it doesn't apply to a 2D. So only apply to a 3D one, as we can see from the computation. So for a 3D vector field, which is given by v, x, y, z, which is 3D space, and for each point x, y, z, I can define a vector associated with a point, which is given by v1, x, y, z, v2, x, y, z, v3, x, y, z. So this is a vector. In other words, if you are given x, y, z, so we should be able to compute v1, v2, v3, give out three scalar values, and we can construct a vector for that particular point. The curl of the v mathematically is given by this. It's given by the notation-wise is a curl curl, and this vector v vector field. You can just eliminate this x, y, z, try to make it simple. Okay, so which is given by partial v3 x, y, z over partial y minus partial v2 x, y, z over partial z time along I direction. Okay, plus partial v1 over partial z minus partial v3 over partial x times j. This is the second component vector. Plus the partial v2 over partial x minus partial v1 over partial y times k. So which means your the curl is a vector, is also a 3D vector. Okay, so which means you have three elements. So three elements are exactly, this is my first element right here, this is my second element over here, and this is my last element for the curl. Okay, so I don't want to talk about this one. You don't have to remember this exactly because it's a little bit hard to remember all the stuff. But as a matter of fact, you can also write the curl of the vector field as somehow like the determinant of a 3x3 matrix, which is given by this. Your first row in the 3x3 matrix, when you compute determinant, is given by I and j and k. Okay, the second row in my computational determinant of a 3x3 matrix will be partial over partial x, partial over partial y, partial over partial, which is just a partial operation basically. And the last row will be just v1 xyz, v2 xyz, v3 xyz. The reason you can do that is if I do the compute the determinant of a 3x3 matrix. Now I don't want to repeat it over here. If you have any question about how to compute the determinant of 3x3 matrix, you can refer to my previous video on the determinant of a matrix. Okay, so what it ends up being that the solution the result will be just exactly what we have over here. The previous one over here is just the same. It's actually equivalent. Okay, so which means hey, you don't have to remember all this, and all you need to know is try to write in the right format of a 3x3 matrix, determinant of 3x3 matrix, and try to calculate all the actual values, actual component for the I and the j and k. Then you are done. Okay, so as I mentioned before, the curl actually talks about the rotation of the field. So divergence talk about how diverges the field. Okay, if the vector field becomes more and more diverged, which means if a particle in the field, and at each point the vector represents velocity. If the field becomes more and more diverse, which means divergence is positive, otherwise it's negative. Okay, the curl has also physical meaning, which means the rotation of the field. Okay, so now let's give you an example showing what that means. Okay, so if I'm giving you a 3D vector field, which is v, x, y, z, which is given by y times I plus 0 times j plus 0 times k. So you can sort of consider this as my y0, 0. So my v1 will be just v1 x, y, z, just the y, v2xyz is 0, v3xyz is 0. Okay, now I can actually draw the vector field. Okay, if you remember, the vector can have idea about what the vector field looks like by actually taking a lot of sample to see how that looks like. Okay, for example, let's start with the case when I have y 0. Okay, so y is 0. Okay, and x 0 and z 0. So which is the origin, this point, right? Then according to here, because y is 0, so it's a 0, 0, 0, right? So this is you don't have any vector associated with it, basically, right? When you move from x to 1, let's say x is 1, y is 0, and z 0 again. So which is this point right here? So you see, because this one does not really depend on this x. So y is still 0, so it's still 0. So which means, hey, I still have 0. You don't have a vector. So any point on the x-axis is always nothing. Okay, right? It's a constant. Doesn't matter because it doesn't rely on. So for the same y. Okay. If I will move up a little bit, let's say my x is 0. Okay, y is 1 and z is 0. So which is somehow over here. So x is 0, y is 1, z is also 0, right? So this is this point. Now here, if you replace y by 1, I have 1, 0, 0, right? 1, 0, 0 is somehow you're moving towards the right direction because your first entry is y. Your vector become 1, 0, 0, which means, hey, my vector along this direction. The reason because my x is 1, but y is 0, z is 0. So this is this vector. So you can also verify for if I have x is even 1, y equal to 1, and z is equal to 0, for example, I still have this point. We still have this 1. So this is the same vector. Okay, as you can imagine, if I'm do 2, if I have like this point is 2, 0, 0. Oh no, this is 0, 2, 0. I get this vector, so on and so forth. Right? The 3 will be this vector, this vector. So you actually can see as you increase this y, actually it's going to go as the vector become larger and larger. Okay, so what I mean by a curve is assume I have a little object right up here. For example, this is my little object. Okay, I want to say, hey, if the particular point on this, let's say that's a beam, right? That's a small object. Let's say that's the velocity I have at each point. The vector field itself represents the velocity of the object. So you can see right here. So this one here is around, let's say here is around 1.5, for example. So the velocity will be 1.5, and this guy is just 2.5. So velocity 2.5. If the object, the top of the object moving at 2.5, say 2.5, this is 1.5. You can see the top moves faster. So you see the object is sort of like rotating this way. Rotation, right? So it's sort of rotation. So if you took a look at rotation, so the rotation is actually along z-axis, right? Along z-axis. Is rotation along z-axis, and also it's a negative direction because if you right-hand roll, if you're rotating like that, your finger actually pointing to that direction, so which is a negative value. Okay, you sort of can say, hey, this is a negative rotation along the z-axis. Okay, all right. Let's see what the computation looks like. If I'm using the curve like this, curve of v, it's like curve v of this. I do I, j, k in a partial I over partial x, partial over partial y, partial over partial z. That's my second row. The last row will be just y 0, 0. So I basically replace this function, these three functions here. I plug this 3 right over here. Okay. If you do the calculation, so I list all the calculations over here, but I will ignore that. You can just read my notes over here. So it ends up having here is the curve is 0, 0, negative 1, which indeed match what we're talking about. The rotation here give us is a negative. It's your right hand rule. It's actually exact direction going that direction. So which is negative, opposite of my positive z direction, which is a negative. Okay, so that's why hey, it's 0, 0, negative 1. So which this one means is rotate along z-axis, and the direction is based on right hand rule. What it means is my finger is here, my thumb is here. This is my other four fingers right here. Here's my drawing is not good. So this one represents rotation along this axis. Okay, of course you could have a negative one if it's pointing the other direction. It's negative. Okay, and the actual value, for example, this one actually rotates how fast it's rotating. If the larger the value is, the larger rotation is. The negative mean is the negative direction. Okay, along the axis. Okay, and the larger the value is, the more rotation we see. Okay, which means it will rotate faster. Okay, so this is what we mean by curve. Okay. All right, so let me give you a little bit more complex example how we compute the curve. Okay, let's see if I have the v is 2y times I plus 3xyz times j plus z squared times k. I want to compute the curve of this 3D vector field. Okay, so according to what we have, so the curve is just the determinant, is the computational determinant of the 3x3 matrix. The first row is ijk, second row is partial over partial x, partial over partial y, partial over partial z. The last row is exactly what we have. All this right in front of this I and j and k we put over there. So we have 2y squared, 3xy, and z squared. Okay. All right. You basically use the first row to actually compute what the reduced by to the determinant 2 by 2 matrix. So I have all this. I don't want to repeat over here. If you do the calculations, you do end up having 0, 0, negative y. Okay, that's our curve for this 3D vector field. All right, I'm going to pose two questions for about this. Okay, about the curve. And first one is, can we find a non-constant vector field that is our zero curve everywhere? Okay. All right. Of course, you can see. Of course, if I do my curve, my vector field is, if my vector field is always constant, x, y, z, for example. 1, 1, 1. Of course, you will have zero curve because there's no rotation here. You can see, right? Also, you do if v is xyz, which is xyz, it's also xyz. You can compute the curve 0. Okay, because I'm doing that, I'm doing all the computation. You get 0, 0, 0. Okay, so it doesn't mean you have to have a constant field in order to yield a zero curve. You can have a non-constant field, but it still have a zero curve. Okay. The second question is, can we find a vector field that is both zero divergence and zero curve everywhere? Okay, right? Of course, you could have my v, again, x, y, and z. Let's say, for example, is 1, 1, 1. Okay, this will give you zero curve and zero divergence everywhere, right? But it's this is a constant vector field. Of course, it's zero divergence, zero curve, right? You could also have a non-zero divergence, a non-constant vector field that can yield zero divergence, zero field. For example, if a v xyz, which is x 2yz, so divergence is just partial first one partial x plus partial the second entry partial y plus the partial last one over partial z. So this gives us 0, right? If we actually compute the divergence, the curve, which is again is the determinant of 3 by 3 matrix, the first row will be I, j, k, and second row is the partial over partial x, partial over partial y, partial over partial z. The last row is what actually we have as the 3 components. So we have here x, we put it here, next to y, put it here, and z, put it here. So we can compute this 0, 0, 0. Okay? That means, yeah, we can have a non-constant vector field which will yield zero divergence, zero curve everywhere. Okay? The other example you could have is a vector field v is yz I plus xzj plus xyk. So if you do the divergence, you can see it's always 0 because for you do partial the first one over partial x, the divergence 0. You do partial xz over partial y, divergence is also 0. And partial xy over partial z, this is also divergence 0. So which means divergence along x, y, z axis, they all 0. If you compute a curve, you also can get a 0, 0, 0. Okay, I don't want to compute this one, but you also get a 0, 0, 0 here. Okay, that's all about the curve.